very much for the introduction. Hi everyone, I'm Shin Watanabe from National Institute of Technology, Gift College. First of all, I would like to thank Jin and other organizers for arranging this seminar and giving me this opportunity. Today, I will talk about theoretical study on multi-channel breakup reactions. These are my collaborators, Ogata-sensei and Matsumoto-san. Okay, I will start with CDCC. As you may know, the CDCC is a fully quantum mechanical method for treating projectile breakup effects. Originally, CDCC was born as a theory for deuteron scattering. Now, it's called three-body CDCC. In three-body CDCC, the total system is assumed to be neutron, proton, and a target three-body model. This figure shows the elastic cross-section as a function of the scattering angle. The dashed line corresponds to the calculation without breakup effect, and the solid line corresponds to the CDCC calculation with breakup. As everybody knows, the difference between these two lines corresponds to the breakup effect. And it is well known that the deuteron breakup effect is important in deuteron scattering. After this success, the three-body CDCC has been widely applied and success in describing many kinds of three-body reactions. So nowadays, the three-body CDCC has been developed mainly in two directions. One is four-body CDCC, and the other is three-body CDCC with core excitation. It's developed by these many authors. These new methods address breakup reactions, including multi-breakup channels. Here, I will explain the multi-channel breakup reactions. Let's consider beryllium-11 scattering, as a traditional three-body CDCC reaction. In this case, the beryllium-11 can be broken up into neutron and a core beryllium-10. There is only one breakup channel. On the other hand, if we consider lithium-6 scattering, for example, the lithium-6 can be broken up into the constituent particle alpha, proton, and neutron, and also alpha and deuteron. This is because the NP subsystem in lithium-6 can be bound. So needless to say, the dynamics of four-body breakup reaction is richer than that of three-body breakup reaction, and its elucidation is important. And each breakup cross-section provides useful information. However, there is a problem in four-body CDCC. In four-body CDCC, a breakup cross-section is obtained as a mixture of different channels. Okay, I will explain this one with the exact case. Okay, this is the discretized breakup cross-section for lithium-6 scattering. The energy is shown with reference to the neutron-proton alpha threshold energy. The ground state exists minus 3.7 MeV, and the D alpha threshold energy is indicated at minus 2.2 MeV. So these are all breakup cross-sections. So if we look at, for example, this bar, this breakup cross-section, there are not only D alpha breakup component, but also NP alpha breakup components because of the discretization of the three-body projectile. In principle, We can decompose the discretized breakup cross-sections by taking an overlap between the discretized state and the exact continuum states. However, it is hard to obtain the exact continuum states for the three-body projectile. Can we decompose breakup cross-sections easily? This is the first motivation of this work. Okay, let me briefly summarize the background and purpose. If a projectile is a three-body system, the continuum states are often discretized in reaction calculations. These discretized states, so-called pseudo-states, are obtained as a mixture of many kinds of channels. The discretized breakup cross-section thus obtained is also a mixture of many kinds of channels. So our purpose is to propose an approximate way of decomposing discretized breakup cross-sections into components of different channels. Okay, let's move on to the model and analysis. So before going to four-body scattering, we consider three-body scattering with core excitation. In this case, beryllium-11 is broken up into not only neutron and the ground state core, but also the neutron and beryllium excited core, like this. Now, these channels are called core ground channel and core excited channel, respectively. This scattering provides a nice analogy to rhythmic scattering regarding the mixture of different channels. Core ground channel corresponds to the D alpha channel, and the core excited channel corresponds to the NP alpha channel, like this. As a merit of this scattering, this is just a simple two-body problem for the projectile. So we can easily obtain the exact continuum wave function. So we can directly compare the exact and discretized breakup cross sections. Okay, this is the total Hamiltonian for describing the three-body scattering with core excitation introduced by these papers. Kr denotes the kinetic energy operator between the projectile and the target. VVT is the interaction between valence neutron and the target. BCT is the core target potential, and it has the non-spherical part. HP is the internal Hamiltonian written like this. Kr is the kinetic energy for this coordinate, and V is the interaction between the valence neutron and the core. HC is the internal Hamiltonian of the core. The projectile wave function is constructed with the particle rotor model. And for the present purpose, we took the distorted wave volume approximation as a reaction part, because this model enables us to calculate both the exact and approximate T matrix elements. We can directly compare these two results. And these are the actual potential we took for the scattering of beryllium-11 plus proton at 63.7 MeV per nucleon. The Saxon potential and Gaussian interaction and optical potentials are taken from these papers. As for the beryllium-10 core, we assume that the deformation parameter beta 2 equals 0.67 and the excitation energy as 3.368 MeV. For the present purpose, we took this small model space. That is, the angular momentum for this coordinate is from 0 to 3, and the core spin is only 0 and 2. Let me review the difference between the discretized and the exact continuum states of projectile. If the Hamiltonian matrix is diagonalized with the basis functions, like Gaussian expansion method, then the continuum states are automatically discretized. This figure shows the energy spectrum of neutron plus beryllium-10 as a function of excitation energy. And now the energy is shown with reference to the beryllium-10 0 plus neutron threshold energy. The excited core plus neutron threshold energy is also shown here. In the present model, two weakly binding states are obtained, and several resonances are also obtained for 5 halves plus, 3 halves minus, and 3 halves plus. They are consistent with the experimental data. On the other hand, if the Schrödinger equation is solved under the proper boundary condition like this, then we have the exact continuum states. The point is that the channel, not only the energy, but also the core state in the asymptotic region is specified before solving the scattering problem, like this. Then we can get these two different wave functions with the same energy. On the other hand, the discretized continuum states are specified by the state number n only. It means the several channels are mixed in a certain pseudo-state. So by using the two kinds of continuum states, we can obtain the discretized and continuum T matrix elements like this. This is the normal T matrix element in the DWBA. Chi k plus and chi k prime minus corresponds to the distorted wave. So if you use the discretized state, the breakup cross-section is also discretized. On the other hand, if you use the exact wave function here, the core ground and the core excited breakup cross-sections are separately obtained. Okay, now we compare these cross-sections. This is the discretized breakup cross-section as a function of the excitation energy. Each bar corresponds to the breakup cross-section of a certain pseudostate. If each breakup cross-section is summed up, we have the total breakup cross-section as 54.8 millibarn. Now that we have the exact T matrix elements, we can directly obtain the continuum energy spectrum like this. If it's integrated over energy epsilon, then we have 54.8 millibarn. So as for the total breakup cross-section, we can obtain the same result. We have confirmed this result. And the next question to be addressed here is the component of the total breakup cross-section. Okay, how to separate the total breakup cross-section? In this work, we would like to propose the probability separation, the so-called P separation. Again, This is a projectile wave function. And here, we introduce the 0 plus probability defined by the squared overlap like this. This probability shows how the ground state core is included in a certain pseudo state. This figure shows the 0 plus probability as a function of the excitation energy. For example, the ground state of beryllium-11 contains the ground state core by 90% like this. All the other states are breakup states. And as you can see, the 0 plus components are scattered by diagonalization. By using this 0 plus probability, now we can decompose the total breakup cross-section into the 0 plus and 2 plus core ground and core excited breakup cross-section like this. However, in this approximation, the core excited breakup cross-section can be finite because of the finite 0 plus component in a certain state. Therefore, we impose this relation. This means beryllium-11 is not broken up into neutron and the excited core below the threshold energy. In this figure, the total breakup cross-section is further decomposed into each spin parity, 1 half plus, 3 halves plus, 5 halves plus, 1 half minus, and 3 halves minus. The line shows the exact calculation, and the circle corresponds to the discretized breakup cross-section. Now, these breakup cross-sections are decomposed into the core ground and core excited breakup cross-sections like this. As you can see, the discretized breakup cross-sections are decomposed into each component very well. Thus, the P separation is found to work for the discretized breakup cross-section. In order to confirm the validity of P separation, we performed the systematic analysis. We prepare other 5 sets of configurations by changing the depth and or the excitation energy of the core. We followed this paper. For example, set 2 corresponds to the original parameter, and it gives 0.5 MeV as the separation energy. In this talk, I will only show these 2 extreme cases, set 1 and 6. A shallower potential gives the weak binding ground state, and the deeper potential gives a tightly bound ground state. Please note that the potential is common for all the states. It means all the pseudo states are also changed with this potential. This figure shows the breakup cross sections for the weakly bound case and the tightly binding case. In set 6, the small threshold energy may lead to the large core excited breakup cross sections, and the tendency is well reproduced. This has a different tendency, but it's also reproduced. So we can say that the discretized breakup cross-section are well decomposed by the P separation, regardless of the configuration. On the other hand, so far, all the resonances constructed in set 1 to 6 appear below the threshold energy. In fact, the separation is trivial for these states. So from now on, we will answer the question, is the P separation still valid, even if the resonances exist above the threshold energy? In order to construct the resonances above the threshold energy, we found that the deeper potential is necessary, like this. Then we are successful in making the resonances here and here above the threshold. This figure shows the discretized breakup cross-section as a function of the excitation energy. The total core ground and core excited breakup cross-sections are shown from the bottom. Now the threshold energy is artificially set to 0.5 MeV here. And the first and the second resonances exist at around 1.1 and 2.6 MeV. As you can see, these resonances make the characteristic peak. However, these two resonances are well decomposed by the P separation like this. So please look at the 5 halves plus. As you can see, the inversion of the core ground and core excited breakup cross sections are nicely reproduced by the P separation. So we can say the P separation works well regardless of the resonance position. By the way, why the P separation works well? We investigated the we investigated the difference between P and gamma defined here in this page. Again, this is a 0 plus probability defined by the squared overlap. This P corresponds to the proportion of the core ground component in a certain pseudostate. And here we will define gamma by this equation. This is the overlap between the nth discretized state and the exact continuum state. So gamma corresponds to the proportion of the core ground channel in a certain pseudostate. And this is the comparison, and you don't have to see this energy region below the threshold energy. The P is not perfect. However, the P reasonably reproduces gamma. Actually, I was very surprised when I first saw this result. And this is the result for the negative parity state, and it's almost perfect. These are the results with different conditions, such as the deeper potential and the smaller threshold energy. In fact, we have confirmed that this relation is realized regardless of the potential parameter, deformation parameter beta 2, and the basis parameters. This may be the reason why the P separation works well. Okay, this is a short summary. We have proposed an approximate treatment P separation for decomposing discretized breakup cross sections. We applied the P separation to beryllium-11 scattering with co-excitation because these two channels coexist. The P separation reproduces the exact breakup cross-section well, regardless of the configuration and or the resonance position of beryllium-11. We also found that P is nearly equal to gamma. This relation is realized. Okay, finally, we will apply the P separation to lithium-6 scattering and discuss the four-body dynamics. We investigated the D-alpha and the NP-alpha breakup cross-section of lithium-6 scattering in the framework of four-body CDCC. We consider these two scattering, lithium-6 plus lead 208 scattering at 39 MeV and at 210 MeV. In this model, we took 1 plus, 2 plus, and 3 plus. And as a first trial, we neglect the Coulomb breakup. As we discussed in the beryllium-11 scattering, first we defined the D-alpha probability, defined by this equation. This is the overlap between the three-body pseudostate and the neutron ground state. This figure shows the D-alpha probability as a function of the excitation energy. Now, the energy is shown with reference to the NP-alpha threshold energy. For example, the ground state exists minus 3.7 MeV, and it contains the D-alpha component by 70%. And as you can see, there are several states have large D-alpha probabilities like this. By using the D-alpha probability, the total breakup cross-section is decomposed into the D-alpha breakup cross-section and the NP-alpha breakup cross-sections. Here, you don't have to focus on the absolute values. Please keep in mind that the NP-alpha breakup cross-section is almost comparable with D-alpha probability. I mean, the NP-alpha breakup cross-section is not negligible compared to D-alpha breakup cross-section. Actually, this result appears to contradict with the findings in the previous work. We mentioned the four-body channel coupling is negligible in the elastic scattering. Please don't worry, we didn't neglect what we mentioned here in this paper. Okay, I will briefly introduce our previous work and summarize the four-body dynamics of lithium-6 scattering. Again, this figure shows the D-alpha probability for all the states in the CDCC model space. Some states have large D-alpha component. And now we categorize these breakup states by using the D-alpha probability. If it is more than 0.5, it is called D-alpha dominant state. And if it is less than 0.5, we call them NP-alpha dominant states. Please note that the number of NP-alpha dominant state is, NP-alpha dominant state is much more than D-alpha dominant states. These are the actual numbers in the model space. Okay, from now on, we investigate the channel coupling effects by switching on and off the 3-body channel and the 4-body channel. This is the elastic cross-section at low and high incident energies. The red and blue lines show the results of full and one-channel calculation, respectively. First, I should say that the full 4-body CDCC calculation reproduces the experimental data well for both the energies. As you know, the difference between these two lines is breakup effect. Okay, in order to estimate the channel coupling effect for these two channels, we neglect 3-body channel like this. There's only coupling between the ground and these states. Then we have this pink line. The results differ little from one-channel calculations. There's no improvement. So we can say that the coupling between the elastic and the 4-body channels is weak. Similarly, we neglect 4-body channel, and we will estimate the coupling strength between these channels. Then we have these green lines. Interestingly, the green lines simulate the full calculation reasonably well. That is, the coupling between these two channels is strong. This means the deuteron in lithium-6 hardly breaks up during the scattering. We call this property d-alpha dominance. And we found that the d-alpha dominance is realized in a wide energy range. Okay, what is happening in lithium-6 scattering? As I said, the coupling between these two channels is weak, but the breakup cross-section of d-alpha and np-alpha are almost comparable. This result may suggest that the coupling between these two channels is strong. The possibility is that lithium-6 may be broken up into 3 particles after breaking up into 2 clusters, like this. The investigation of this hypothesis is an interesting future work. So in summary, we have proposed an approximate treatment P-separation for decomposing discretized breakup cross-sections. We applied the P-separation to beryllium-11 scattering with co-excitation because these two channels coexist. The P-separation reproduces the exact breakup cross-section well, regardless of the configurations and or the resonant position of beryllium-11. We also found that this relation is realized. So our conclusion is that this method can be an alternative approach for decomposing discretized breakup cross-sections into components in 4 or 5-body scattering, where the strict decomposition is hard to perform. Okay, that's all. Thank you for your attention.